Today, we're going to continue solving trigonometric equations. We're going to add some stuff to what we did last time when we were solving trigonometric equations. The core things that we need to do are to get the reference angle and then put the reference angle in the appropriate quadrants. Today, we're going to add the third piece where we get all the solutions. When we put the reference angle in the appropriate quadrants, that's getting us two solutions. So for example, where cosine is positive, cosine is positive in the first and fourth quadrants. So we put the reference angle in the first and fourth quadrants. That gave us two solutions. That's going around the circle one time. But now I want to get all the solutions. So I'm going to ask you to solve cosine of theta is negative root 3 over 2. And I didn't restrict theta in any way. I want all the solutions. We know there are infinitely many, so we're going to have to summarize what our solutions look like. Let's go through the first couple of steps. We need to get the reference angle and then put the reference angle in the appropriate quadrants. So the first thing, to get the reference angle, we've got cosine. Our reference angle will be the cosine inverse of root 3 over 2. This is one that we happen to know. We know that since, let's see, cosine of root 3 over 2, cosine of 60 is root 3 over 2. So we know that our reference angle is 60 degrees, or pi over 3 radians. No, cosine of 60 is a half. No, sine of 60 is a half. Cosine of 60 is root 3. I don't know if this is a more coffee problem or a less coffee problem, but I kind of know which solution I'm going to be applying. Someone tell me what the cosine inverse of root 3 over 2 is, since apparently I have forgotten. Is it 60 or is it 30? Or is it 45? I'll put that out there. $30. I hit Control C on my mind. So we got a 30-degree reference angle, right? Yeah. That's the first thing. We get a reference angle. We ignore the negative parts. We just go for the reference angle. Just take the value root 3 over 2, not the negative root 3 over 2. And now we're going to put the reference angle into the appropriate quadrants. So now cosine is negative in the second quadrant and the third quadrant. So I need to put a 30-degree reference angle in quadrant 2 and quadrant 3. So 30 degrees in quadrant 2 is 150. And 30 degrees in quadrant 3 is 210. Those are our first two solutions. If we were just looking for the solutions between 0 and 360, we just got to get the 150 and the 210. However, we know there are infinitely many solutions. So all we have to do now is take that 150 and get all the other angles that are coterminal with 150. So here's our angle 150. So we have, let's see, 30 degrees in quadrant 2. We know if we go start at the positive x-axis and go just up to the 150, that's 150 degrees. But there are infinitely many coterminal angles. So I can go not just straight to 150, I can go all the way around. So I can start at the positive x-axis, go all the way around, pass go, collect $200. And that would be 150 that we started with, plus one full circle. So we can do another circle after that. So I can do not just once around, I can start at the positive x-axis, go around not once, but twice. So here we are, 150 plus 360, but I can just keep going. Once, twice. And there I have 150 plus 2 full circles. This is because the cosine of theta has a period of 360 degrees. So what we can do is we could say that the solutions are 150 plus any integer multiplied by 360. So to get all the solutions, we'll say plus n, 360n, plus 360 times n, where n is an integer. And the same thing can be done with 210. I can't put too many more circles up here. We'll start to get busy. But we can take 210 degrees plus 360 times n, where n is any integer. And here are all the solutions for theta. 150 plus something times 360, 210 plus something times 360. N can also be negative. N can be any integer, and this is positive or negative. Because if I start at 150 degrees and go back start at 150 and go backwards 360 degrees, I'm still coterminal with 150. So possible solutions, it's like 150 is in the middle. And then I can add 360 a bunch of times. So 150 plus 360 is 510. So that's a solution. I spelled 510 wrong now. I can add another 360. 870 is a solution. And this goes on forever because we can add any number of circles. But I could also take the 150 and subtract 360, go backwards a full circle and be at negative 210. And if I subtract another circle again, we'll be at negative 570. And this will go on forever in that direction. These are not all the solutions. We've also got the 210. So we also have 210 plus all the multiples of 360, all the integer multiples of 360. 210 plus 360 is the 570. And we're going to start to notice some patterns probably. 570 plus 360 is 930. I have to stop there because that's like way past my bedtime. But I can take a 210 and subtract 360 a bunch of times. So negative 150 and subtract 360 again. And all we're doing is adding and subtracting the period. So negative 510. And then this will go on forever backwards as well. We knew there were an infinite number of solutions. We want to make sure that we list them all. So to get all the solutions, once you get the reference angle and put the reference angle in the appropriate quadrants, then you just add an integer multiplied by the period. That's how you switch just the first two to all the solutions. Add an integer times the period. N is not the period, 360 is the period, N is the integer. So 360 is the period, N is any integer. If we're doing the problem in radians, I didn't specify whether I wanted radians or degrees in this case. I started with degrees because I was not sure of my arithmetic skills, especially after forgetting what the cosine inverse of root 3 over 2 is. But if we wanted to do the problem in radians, we would just convert everything to radians. You can do the problem in degrees in your mind and just write down the radians. So we would start off by saying cosine inverse of root 3 over 2 is 30 degrees, which is pi over 6 radians. We still want to do the pi over 6 in quadrant 2 and quadrant 3. And so that still gives us our two base answers of 5 pi over 6 and 7 pi over 6. But now we're going to add integer multiples of the period. But now the period, since we're in radians, is not 360. The period is 2 pi. So we'll add 2 pi times n. Where n is any integer. I forgot to include that in my example above, so I need to build an annex. I'll put a door in between those two. So 2 pi is the period when we're dealing in radians. N is still any integer. So we can solve the problem in radians. We can think this whole thing in degrees. We just see 5 pi over 6 is 5 copies of pi over 6, which is 30 degrees. This particular page of the notebook has a lower speed limit than the other ones. I can only write so fast on this page. Other pages have higher speed limits. It's really weird. But that's the next step. So last time we learned to find the reference angle. Then we use the sign to determine the appropriate quadrants. And now we're just adding integer multiples of the period. So just plus the period times n, where n is any integer. So that adds this part. Any questions? All right, let's make a small change to what's going on here. We're going to start doing extra stuff going on. We're going to start thinking in terms of inverse operations in reverse order. We're still going to focus on getting the, when it comes to the trigonometry function, we get the reference angle, we put the reference angle in the appropriate quadrants, and then we get all the solutions. So that's just for the trig function part. That's just for the trig function part. So let's take a look at a very small variation of this function, or this equation. So instead of cosine of theta is equal to negative root 3 over 2, I'm just going to change this to cosine of, what should I use? I'll just go with 2. 2 theta. 2 I already have. Let's go 5 theta. Go big. Let's suppose that the cosine of 5 theta is negative root 3 over 2. We still want to find the reference angle, but we're not going to be finding the reference angle for theta. We're going to be finding the reference angle for 5 theta. A lot of the stuff is still going to go look the same. We're not finding the reference angle for theta. We're finding the reference angle for 5 theta. I ignore the negative because I'm finding a reference angle, and the reference angle is still 30 degrees. Now, before we jump the gun and start dividing by 5, we need to put the reference angle in the appropriate quadrants. So it's 30 degrees, and since this is negative, this is in quadrant 2 and quadrant 3. We don't want to go dividing by 5 because we haven't finished the trig function part. We've just found the reference angle. We haven't put it in the appropriate quadrants. We haven't written down all the solutions. We're not done with the trig function parts. So in quadrant 2, I did degrees. So in quadrant 2, we were dealing with a 150-degree angle. Or 210 degrees. Now we're at kind of a tricky thinking part. Are we going to divide by 5 yet? Or are we going to add the period yet? I don't know how your mind is going to work this out. But when I put, so this is the way that I think about it. So let's just think about this is just me thinking about it. So the 150, that's 30 degrees in quadrant 2. We're not solving for the theta yet. We're solving for 5 theta. So this is still encumbered. This is still a 5 theta that we're solving for. Because the 30 degrees is a reference angle for 5 times theta. And so I'm just going to say, do the normal thing. The third step is to get all the solutions, plus 360 times n, where n is an integer. But we weren't asked to solve for 5 theta. We were asked to solve for theta. So theta, if I divide everything by 5, 150 divided by 5 is 30. 360 divided by 5 is 72. 210 divided by 5 is 70. No, it's not. What am I thinking of? How did I come up with 70? That's weird.
40.
I totally know that 210 divided by 5 is 42. I didn't need to use, oops, I did need to use a calculator. So 210 divided by 5 is 42. Thank you. Also, someone told me. And then 360 divided by 5 is still 72. Where n is any integer. So remember what's happening is that before we take the cosine, if we look at what's happening to the theta, the first thing that happens to theta is that we multiply by 5, then we take the cosine. So 30 degrees times 5, I knew 5 was a bad idea going in, but I'm like all prime numbers. Should just gone with 4. What's wrong with 4? Next time use 4, mental note. I'll forget. I'm going to use 5 again because it's all prime numbers and that'll make me happy. So the first thing that happens to this 30-degree angle for theta is it gets multiplied by 5, becomes 150, and the cosine of 150 is negative root 3 over 2. The first thing that happens to this 42-degree angle is we multiply by 5, get 210, and the cosine of 210 is also negative root 3 over 2. If we look at the cosine of 5 theta, the period is 360 divided by 5, and that's the 72. So the 72 degrees that shows up here is the period of cosine of 5 theta. The 360 that I used before, 360 is the period of cosine theta. But the 360, I was using 360 up here because we haven't divided by 5. I use 72 down here because we have divided by 5. In my mind, it works better to write plus 360 times n and then divide by 5 than to divide the 150 and the 210 by 5 and add 72n. It's exactly the same thing because it's just multiplication and addition. But in my mind, it works better if I think of adding the 360n and then dividing that by 5 as well. In your mind, it might work the other way. You might say 5 theta is 150, 5 theta is 210. I'll divide those and get 30 and 42, and then add the period, which is 360 over 5 or 72. We both end up at the same place, but there's 2 different paths to get there. Did you add the 360 and then divide by 5, or add the period of 72, which you also get by taking the 360 and dividing it by 5?
Is n just the number of times you go around the circle? Is that what it's supposed to be represented?
Yeah. Yes.
So does it get divided by 5 also?
We did divide it by 5 when we divided the 360 by 5, because the 360 and the n are multiplied together. I don't have to divide them individually. If you find $30 between 2 people, you don't have to divide it up twice. If you have the $30, at $30 is like 3 times 10. You don't have to divide the 3 and the 10 by 2.
Understood. Thank you.
Any questions? So when you're solving the trig functions, that third piece, adding multiples, integer multiples of the period, is part of doing the trig function. Everything else is just going to be extra. Any questions? See, what I should have done to avoid all these calculations that I kept messing up is I should have done the problem in radians. Because in radians, fractions are easy. We end up with fractions, but fractions are easier to divide, especially when we're going to get nice ones like pi over 6. So in radians, we would say the reference angle is pi over 6, and we're going to put pi over 6 in quadrant 2 and quadrant 3. So pi over 6 in quadrant 2 is 5 pi over 6. Pi over 6 in quadrant 3 is 7 pi over 6. This is not theta, this is 5 theta. And I can either add multiples of the 360 or multiples of 2 pi, or I can divide by the 5 and then throw on all the extras. At some point, we got to get all the solutions. We can either put them on now or put them on later. In my mind, for whatever reason, it works best when I say plus 2 pi times n and then divide by 5. Dividing by 5 is super easy because we have fraction multiples of pi and they're going to stay fractions. So when we divide by 5, 5 pi over 30 is just pi over 6 plus 2 pi over 5 times n. 7 pi over 6, well, I don't have anything that cancels. If I divide 7 pi over 6 by 5, it's just going to be 7 pi over 30 and plus 2 pi over 5 times n, where n is any integer. So all you fraction haters out there are incorrect. Life is easier if you start using fractions, especially if you're just going to be multiplying and dividing. Any questions? All right, so it could be that we wrote down 5 pi is equal to 5 pi, 5 theta is 5 pi over 6, 5 theta is 7 pi over 6 divided by 5, and then just added the period, which is 2 pi over 5. It would look the same. So you might say, no, you got to divide first, Leach, that's the way. So you'd write pi over 6, and theta is 7 pi over 30. And you say, but the period is not 2 pi, it's 2 pi over 5. So then you write plus 2 pi over 5 times n. Get you to the same place. Any questions? All right. Let's take a look at another variation and then start thinking about this in terms of inverse operations in reverse order. Leave a space. I still want the cosine, even though the 5 theta didn't work out, I'm going to continue to use 5 theta. And it's still going to be negative root 3 over 2. This one's going to be extra sneaky because what I'm going to do now is I'm going to put something in front of the cosine. I'm going to multiply this whole thing by negative 4. So now there are more things that are happening to theta. There's this multiplying by 5. We saw how to deal with that. There's this cosine. We know how to deal with that. Reference angle, quadrants, add the integers, the period times the period. And there's also this multiplying by negative 4. We've got to undo all of these things. Let's think about the order of operations in this expression. Now, when I say let's think about the order of operations, I do not want you thinking of PEMDAS. PEMDAS is trash. Get rid of that. I'm on record. It's being recorded. I've said it in other recordings. PEMDAS is trash. If you're telling people PEMDAS, you need to knock it off. That's bad. It's unhealthy. It causes fights on the internet, all that stuff. We're going to use the order of operations and read what's going on in this expression. Because first of all, we have trig functions in our equations now. And so where's the trig functions in PEMDAS? That's what I thought. PEMDAS is trash. It's no longer any good. It's not that it will give you wrong answers. It's just a horrible way to think about that. That's computer think. That's how you talk to computers, because computers are dumb. You're better than that. Don't try to learn math as if you're a computer. First of all, you're better than that. And second of all, you're really much worse at the way that computers do the calculations. So let's think about what will happen if we plugged in a theta. What happens to theta to turn it into a negative root 3 over 2? Well, the first thing that happened to a theta is it gets multiplied by 5. So I'm going to make a note because I think it's multiplied by 5. And then the second thing that happened is once we have 5 theta, we find the cosine of 5 theta. And then the third thing that would happen if we're plugging stuff in is we multiplied by a negative 4. So this is the order of operations that took theta and turned it into negative root 3 over 2. This is what we did to turn theta into a negative root 3 over 2. Now we're going to perform inverse operations in reverse order. This is not a new thing. You've always done this. This is where, when you were told to do the same thing to both sides of the equation, that's all we're doing. We're just including the information that says what order to do the same thing to both sides of the equation. So we're going to come up with a plan. And we're going to turn the negative root 3 over 2 back into theta. And we're going to do inverse operations in reverse order. So first, we're going to undo this multiplying by negative 4. That was the last thing that happened. It's the first thing that we undo. And we do that just by dividing by a negative 4. Next, we're going to undo the cosine with a cosine inverse. This involves 3 steps. Reference angle, put it in the quadrants, get all the solutions. Reference angle, quadrant, period. That's 3 things that are involved just in that cosine inverse. And then the third thing that we're going to do is take care of the multiply by 5 with divide by 5. And that'll take a negative root 3 over 2 and turn it back into a theta. Inverse operations in reverse order. So that tells us what we should do to both sides of the equation and what order we need to do those things. So first, we'll divide by the negative 4. So that'll give me cosine of 5 theta is negative root 3 over 2 divided by a negative 4. That makes it a positive root 3 over 8. Next, we're going to do the cosine inverse thing, which has 3 steps. That involves 3 things. That involves the reference angle, the quadrants, and the period. So the next step is cosine inverse, which is 3 steps. I'm going to find the reference angle for 5 theta with the cosine inverse of root 3 over 8. Now in this case, I lost my root 3 over 2 that I knew, and now it's some funky root 3 over 8. So I'm going to have to go resort to the calculating machine. Calculators in degrees, so I'm just going to do the problem in degrees. That won't be a disaster at all. So cosine inverse of root 3, close parentheses, divided by 8, close parentheses, is 77.5 degrees, let's call it. Now notice we're going to put this is the reference angle, and we have to put it in the appropriate quadrants. Reference angle, quadrants, period. That's what's involved in that inverse trig function. In the original, we had a negative. But once we get rid of this -4, this is now positive. So I'm going to put the 77.5 in quadrant 1 and quadrant 4, where cosine is positive. So I'm going to have 2 answers. 77.5 in quadrant 1 is just 77.5. And 77.5 in quadrant 4 is just going to be 360 minus 77.5. So 282.5. Nearest 10th folks are like, oh, okay, that's cool. Significant figures folks are like, oh, dude, what are you doing? Now, these are not thetas. These are 5 thetas. So I have to add full circles. Then we'll divide by 5. So the 77.5 divided by 5, 15.5. And we know the 360 divided by 5 is the 72. And then I also need the 282.5 divided by 5 is 56.5. And the period is back down to 72. Any questions? We're solving by doing inverse operations in reverse order. Rather than just looking at the equation, and trying to figure out what to do next, we actually write down what's going on in the expression so that we can figure out inverse operations in reverse order. We can figure out what our plan is going to be before we start doing any work. The first thing we did was we divided by the -4. Then we did the cosine inverse thing. And then we did the divide by 5. Any questions? This only seems like it's a lot to remember because it's a lot to remember, and you have to remember all of it all the time in perfect detail. And you might not have been given a kind of a general purpose method for solving equations by doing inverse operations in reverse order. I know there have to be more teachers that are out there talking about inverse operations in reverse order as a general purpose equation solving method, but I don't personally know any. There have to be. There's no way that me, I'm just some schmuck. There's no way that me, I just some dude, has this idea that no one else is thinking of. There's got to be someone out there writing a book with this idea, where they're thinking that algebra is just arithmetic. Let's teach algebra just like our arithmetic classes, based it on operations and stuff, instead of trying to teach it like a website. 8 simple tricks to smash your next math test. That's how we've been teaching algebra for so long. Most teachers would agree. It's like, oh, there's something wrong with the way that we teach algebra. It's like, oh, great, let's do something different. And they're like, oh, but no, let's just do the same thing. I'd be really bummed if I wrote the book, because I'd be worried that I want to sell out, because I would hate to like write a book and then start charging my students for it. I think that's messed up. If you write a book and you're collecting royalties on that book, you better be just giving it to your students. Because that'd be like making a product, getting people addicted to it, and then making money off of them because they have to use your product. Does that make sense? So if I write a book, I would never find a publisher, because they'll be like, oh, we're going to charge this many dollars for your book. I'm like, oh, no, you're not. You're going to charge $0 for it. And then I would just publish it on the internet for free. And some publisher would sue me, I guess. Any questions? Not about math books and stuff. All right. So a thing to note about this inverse operations in reverse order. This works because the variable only appears once in your equation. When the variable appears more than once, we can't just list the operations that are happening to it. So in that regard, this is restrictive. But if we take this as if we really want to focus on operations for any of you that are teachers that are going to have a problem with what I'm saying, how inverse operations in reverse order is the way. It's like, well, what about even just a general quadratic, ax squared plus bx plus c equals 0? If the variable appears more than once, then we can't do inverse operations in reverse order. We have to. This only works when we have the variable appears just one time. So if you're going to come at me, bro, with quadratics, remember that you're also going to be teaching the quadratic formula, and that is exactly following inverse operations in reverse order, because we complete the square so that the variable appears only once. And so don't use that one, use something else. And at that point, everything else becomes kind of a niche problem. We have to do something else. If we can't do inverse operations in reverse order, then we can learn categories that fit for those kinds of equations that will get us to this point, inverse operations in reverse order. And when we think about the scope of the problems that we deal with in algebra classes, we can get away with this quite a bit. And then we can cast everything else as a niche problem. And then instead of the order of operations being this stupid PEMDAS BS, we'd be able to talk about the order of operations. We'd be able to read expressions better so that we can think about what's going on and then undo those things. That's why I think this is the way. Anyway, that's just me selling a book that I haven't written that doesn't even exist yet. All right. So if we have other things that are going on, for example, if I have, let's say, I'm just going to add on the outside. Notice that what I've done here is I've done multiplication before cosine and multiplication after. If I have, let's say, another term, let's say, how much is root 3 over 8? I have one written down, and then I can't remember where I wrote it. And so root 3 over 8 is 0.216. So I can only add, like, let's say, a half. Oops. Oh, I can do 1. Let's suppose that I had the equation 1 minus 4 cosine of 5 theta is equal to negative root 3 over 2. So now I've included another operation. We have to think about, we want to do the same thing to both sides, but we need to read what's happening to theta so that we can come up with the appropriate plan. The first thing that happens to theta, we start with theta, and then the first thing we do is we multiply by 5. Next thing we do is we do the cosine of 5 theta. We take the cosine of 5 theta, and then we multiply by negative 4. Because multiplication goes before addition in the order of operations. And then we add 1. I know it says 1 minus, but we multiply by negative 4, so we just think of this as adding 1. And that turns theta into a negative square root of 3 over 2. So if I want to come up with a plan that'll turn negative root 3 over 2 back into theta, first, we're going to have to undo this plus 1 with a minus 1. Second, we can do the plan that we had before. We can divide by a negative 4. Third, we'll do the cosine inverse thing. That has 3 steps: reference angle, quadrant, period. And then finally, we'll divide by 5. So that's our inverse operations in reverse order. Here's just us reading what the function is telling us to do. That's all this is. It's code for do stuff to theta. First multiply by 5, then take the cosine of 5 theta, multiply the cosine of 5 theta by negative 4, and then add 1 to the result. Any questions? So you just start with root 3 over 2, or negative root 3 over 2, and subtract 1. This is an irrational number, so we're going to have to hang on to it. Then the next thing is to divide by negative 4, also an irrational number. And now we can do the cosine inverse to find the reference angle. Notice I'm not writing any of these numbers down. I want to keep track of it all on the calculator. I don't want to plug rounded off information into my problem until I get to here, 62.19, I'll call it 62.2. Then I'm going to have to take the 62.19 and put it in the first and fourth quadrants. Then I can divide by the 5 and add the 72n. So theta. So I need the 62.19. I need that divided by 5. So that's going to be a 12.4. And I happen to know that the period is 72, so plus 72 degrees times n. And my other answer well, I'll need 5 times this again. I need to put this in the 4th quadrant. So that's 297, and then I need to divide it by 5. So here are our infinite number of results. The place that you want to be as far as knowing how to do this is to look at the equation, read it, come up with your plan, and write down the solutions. So this is what you need to write down. The reason that we do math classes is to get to the point where we don't have to do all the math, where we don't have to write down all the stuff in the middle. That's why I say things like show your calculations. And if you're like, oh, dude, I did all my calculations on a calculator, and so I just wrote down the answer because I was able to read this and come up with a plan in my mind. So this can take place in your mind. That's the goal. You want to think this. Any questions? Comments? Snide remarks? Now that algebra is going away from community colleges, I have tons of ideas about how better to implement thinking about algebra. All right. I have a feeling that if I try to make a Kickstarter for this book, it would not fly. People would be not interested. But if I learn how to do something like make dice or like a cool D&D supplement, maybe I can kickstart that, and one of the chapters will be algebra as arithmetic, and just kind of like sneak it in there. Kind of sneak it in there. I'm gonna have to start working on some D&D material. That does a little bit better on Kickstarter. That seems deceptive. I probably shouldn't have to jump through those kinds of hoops, but there it is. Any questions, comments, deep thoughts, snide remarks, astounding observations? All right, that's going to do it for today. That's going to do it for this week. Everybody have a good weekend. I'll see y'all on Tuesday, and thanks for playing.